in 1988, when I have completed my PhD under the supervision of Professor Szolgay, Arpad told me that you are an independent researcher. You can do what you want. The floor is yours. And I was a bit, I was surprised and a bit afraid that what should I do? And then I spoke to Tamás, and at that time, as Arpad mentioned, that Tamás was the leader of his group, and yes, he told me that these cellular neural networks projects, which outlined by Professor Chua in Berkeley just in 1988, he published in IEEE Transaction. And why was it important and interesting? Because it has a low dissipation, as András mentioned here, and the second issue was extremely fast. The estimation said that the chip implementation, especially the first chip which was implemented by Hubert Harer in Munich, it has around tera operation per second, which is 10 over 12, which is huge. And based on Tamás and Leon Chua made theoretical architecture, which was the CNN universal. Universal in that sense, this is a Turing machine. This can do everything what you can do in a Turing machine, not with an equivalent speed and dissipation. And I have joined this group, and we have developed several things to use this paradigm. We have developed the first add-on board, which was simulate or emulate 1 million pixel or virtual cellular cells, which was a huge. And yes, and we these theoretical implementation opened a race of the designers to do a better, larger, more effective, more user-friendly chips. And finally, at this red camera below, you can find an industrial application, which the designers, the players of this race was the Spanish group in Seville, the Finnish group in Helsinki, and third player is the University of Manchester. Peter Dudek is the author of this. But what was it has a very nice features and possibilities, but it has some limitations. The accuracy was around 6-7 bits. The homogeneous technology in analog VLSI, it is fairly not trivial, even today not trivial. That's telling the truth. And therefore, Tamás proposed to make an implementation on digital this architecture, and knowing that we are not able to decrease the dissipation in digital as in analog was. And we are losing a lot of speed, but we may gain some accuracy advantage. That means 16 or 32 bits we can implement. This is one thing. Then another thing is that nonlinear templates, larger neighborhoods. These templates says that if you want to simulate a physical system, these parameters include the physics of the system. And we have developed two implementation. One was with Ákos Zarandi, the castle architecture, and another with Zoltán Nagy, the Falcon processing unit, which was implemented in a FPGA, and several things we could program, which was not possible in analog implementation due to the VLSI technology was not so strong. And based on this, and Tamás encouraged us to, how can we implement some data flow or high-level algorithms in 2D, two-dimensional arrays. How can we map this problem to two-dimensional array, keeping in mind that the goal is to minimize the area, because the area, we have to pay for area in Foundry. The accuracy, the speed, the dissipated power, and the bandwidth between the processing units and the memory, this is also a critical issue. And limits, of course, we have certain limits. We have a limited number of processors on a given silicon area. We have a limited memory size, and we have on-chip memory, and we have off-chip memory. Considering the off-chip memory, we have a bandwidth limit, which is also a critical issue. And we have, next I want to show some examples which we could solve. These are all problems are from some aspect, they are difficult from computational point of view. This is the computational fluid dynamics. This is there is an obstacle, and there is a flow. High-speed flow is coming from left to right, and the shock wave is can be detected, and it is a computational difficult problem. Even if we could solve this in 2D, not in 3D, but this is nevertheless, it is a computational difficult problem, and we could solve it. Another example, which is we have get a simplified two-channel retina model from Berkeley. Tamás son was working in this project, and they could give us a biological, a measured biological parameter, a two-channel retina model. And how can this, they tried to simulate it, and it was, I don't know, 1 or 1.5 day simulation of a step function, which is the simplest thing. And we tried to implement it. You can see with different timing and timing parameters. This is the structure of the processing or core architecture. That means a single neuron has a diffusion type, Gaussian type, and interlayer part components, and we could simulate it or emulate it. And the question was, and it was important for speed up the process, which kind of accuracy is feasible? And we compared the floating point which was terribly slow. Operation to different bit accuracies, and it turned out that 20-bit accuracy seems to be quite good approximation of the floating point accuracy, which for us it was the accurate solution. The next example is the brain signal processing. Yes, thank you very much. And that the neurons communicate with spikes, and but we have several brain signal measurement units, and we have to parallel operate it and classify it, and this is the but the next topic is the so-called Sense and the Void project, where there is a red airplane with red dot, and a UAV, unmanned air vehicle, and we have to avoid the collision with this airplane. And in the UAV, an extended Kalman filter is trying to estimate the trajectory of the normal airliner, and it was implemented in a Spartan 6 FPGA. Why Spartan? Because the silences are more complex, but they dissipate more, and we have to do everything on board and to keep the dissipated power limited. Ákos was the leader of this project, and yes, last but not least, we have the problem to identify for handicapped people, identify objects and grasp it. That means an artificial robot arm should have a camera. The handicapped people have a head camera, and he select the object to grasp using seeing on this object, and we have to define a boundary of this object and identify. Why we should identify? Because if I want to catch, I have to define the force. How okay. We have learned, and we could use several things from original cellular neural networks and extend it to many core architectures, and we could solve complex problems, and these problems could be defined in high-level language. Nowadays the RISC-V ideas are followed, and last but not least, in the heart of Tamás, in the middle, was that doctoral school, and these new scientific results provided several doctoral theses, which was very important for us and very important for Tamás and also for us. Thank you very much for